Okay, so here is the rest of the lecture. Sorry, I forgot to record at the very beginning, but I'm going to quickly go over what we did. Go back to screen share. Here was our quiz. First, we wanted to find the slope of the secant line between the points, where f of x was x squared plus 2x. I used f of b minus f of a over b minus a. I plugged in x is 2 and x is negative 1, and found my f of b minus f of a over b minus a, worked it all out, and I got 3. Then I want to do the tangent line, and again, I did f of b minus f of a over b minus a, but now if I want to go near 3 and you want the tangent line, you want to get really close. So as I mentioned when it wasn't recorded, that if you want 2 decimal places of accuracy, it's better to use more than 2 decimal places for the input so that the output is more likely to have better accuracy, and then you can round to 2 decimal places. So I did f of 3.00001 minus f of 3 over 3.00001 minus 3. And that should give me my 2 decimal places, you know, and better maybe. All right, now question.
Larry.
So,
Question?
Larry, quick question. Would you ever have to graph the two equations since you're finding the slope? Would you have to enter that into like a graph itself, or no? Not really.
Not really.
Okay.
I mean, the only reason why you might graph it is for checking your work.
Hmm.
You know, you can graph it, take a look at it. Hopefully you all know that x squared plus 2x is a parabola. You could take a graph, and then you can, when you're done, you can see if the tangent line actually looks about right. So for
Okay.
checking your work, graphing is a good idea, but you don't have to graph. Does that make total sense?
Yeah.
And there was another question, I think?
yeah, so I noticed, well, I was using Desmos a little bit to like see where these points were hitting. And I noticed that if I put too many decimal points in, like if I did the 3.000, like once I got past 4, I would end up with a 0. Like it
Okay,
would
I
end
don't
up,
recommend Desmos for arithmetic. Desmos is great for graphing. It's not great for arithmetic. I like Google for arithmetic, and I'll show you
okay.
how I do that. It's a lot easier too.
It was a different kind of problem, but like the same concept. I just kind of wanted to see what it looked like.
Uh-huh.
I just kept ending up with 0, so maybe it just wasn't going out far enough. Is that
Yeah. Yeah, Desmos I don't think can handle a lot of decimal places.
okay?
I think that's the problem. Yeah, but I'll show you how you can use Desmos if you want with this at the end to check your work, okay? Which you won't be able to do on the test, by the way. No Desmos on the exam.
Oh yeah, this
So
was just on the homework.
yeah, but for the homework, I can show you how to check your work on this, and it's pretty easy. So let me do this f of b minus f of a. Let's finish this problem out. And so we need to go f of 3.00001 minus f of 3 over 3.0001 minus 3. So let's find f of these values. Okay, so first thing, f of 3.001, 4 zeros and a 1. We have x squared plus 2x. So up here, I'm just going to put 3.00001 and then squared, and then plus 2 times 3.0001. Okay, and can you see? I'm never sure whether you can see when things pop up. Can you see 15.0008? Can y'all see that? Yeah. Okay. Again, sometimes I don't know what you can see when we're sharing that stuff. So it's right. So 15, 3 zeros, and 8. So let's write that down. F of 3.00001 is equal to 15.0008. F of 3 I can do in my head because that's going to be 9 plus 6 is 15. Any questions on that? So what I can do, I'm going to just stick a parenthesis right here. I'm going to subtract 15. And then I'm going to divide by 3.0001 minus 3. And what do I get? Can you see it? Hopefully you can see it. 8.0001 to 2 decimal places, that's 8. Okay, now I want the equation, not just the slope. So again, you are required to know, algebra. This is beginning algebra. Is that if you have a slope and a point, how do you find the equation of the line? Everyone's quiet.
Wouldn't it be
Points.
y minus y1 equals m parentheses
Right.
x minus 1?
X minus, yeah, or X minus X1. Exactly. So that's what we're gonna do. So then our equation is y minus, and y1 is 3, because because that's our, sorry, y1 is not 3, y1 was 15, equals m, which was 8, x minus x1, which was 3, and that's good enough, by the way. My rule, by the way, unless it's a word problem and you actually have to answer the question or whatever, is that once you've done the calculus, you're done. You don't have to continue on. You don't have to like make it look different or something, but that's good enough. Okay, for exams and quizzes.
I have a question.
Uh-huh.
So like on the homework, because of the table, like I used the numbers around 3, so I kind of did that here. You
Mhm.
still get 8, is that okay?
Oh yeah.
Like
Well,
I
that's
used
what I did. I used a number around 3, didn't I? I used 3.00001.
exact of a number. Yeah, okay.
What's that?
I use like
Yeah,
2 and 4.
Well, 2 and 4, if you use 2 and 4, you may not get 2 decimal places.
But it still like rounds to 8. I don't know. That's
Yeah. So let me tell you, Alexi, you got lucky.
Yeah, that's true.
Yeah.
Probably.
2 and 4 is way too far away from 3 to
Okay.
trust yourself. If you want 2 decimal places, you should at least do 2 decimal places. So if you did 3.01, then that might be okay. Does that make sense? 2 and 4, most of the time it'll be wrong. You got lucky. So that's really important, is that if you want 2 decimal places of accuracy, don't do 0 decimal places is what you did. You did an integer difference. Does that make sense? Yeah. So has to do with decimal places, is that, think about that. And then what I recommend is if asked for a certain number of decimal places and there's gonna be some arithmetic to do, add a couple more. So that's why I used 0.00001, and it's easy. Again, throwing it into, I like the Google search bar because to me, that's the fastest calculator because it's there waiting for me. And how long did that take? It was quick. So that's just a note. A whole number away is actually pretty far. Okay, unless you're dealing with, say, astronomy, where you're talking about, 1 meter away versus, how far the sun is from the earth, and you go 1 meter difference. That's pretty good. But for normal things, you want to do some extra decimal places. Okay, and just a note, if you want, it's 8x minus 3 plus 15. So if I go to Desmos, and it was x squared plus 2x, was it? I think so. So if I graph that one, and then to check your work, that was y is equal to, let me remember again, 8x minus 3 plus 15. And we probably need to zoom. Well, it's probably fine. then we can see right there, the tangent line and the curve look pretty much the same, don't they? And that's what you want. So Desmos is telling us, yeah, what we have, you know, is pretty likely correct. Where the line is like not even close to the curve, you should worry. And if it like crossed out some that way or something, you should worry a lot. All right. So I have one person trouble with audio. Are you having trouble with audio also? Sorry about that. Yeah, I think it's I don't know, I think it's my computer microphone. I can't do much about it, but let me know if you don't hear me, ask me, and I'll repeat. That's your job. Let's just say, what do you say? But do you understand how you can use a graph to check your work? Okay, Desmos doesn't tell you the equation of the line, the tangent, but it does give you a good idea whether you got the problem right if you're doing homework or something, because it's looking pretty good. This curve and this line look like the same at the point we're looking at. Any questions on the quiz?
Yes, please.
Yeah, question?
Yes, please. So when we're
Yes.
talking about the function being at 3, can you get some clarification on that? Is that x equals 3? Is that the point
Yeah.
3, 3, or is it as the limit is approaching 3? Or I'm not really sure.
Okay, it turns out for this particular example, those mean exactly the same thing. But today, section 2.2 is all about when things might go wrong. But in this one, it doesn't go wrong. So at 3 and when the limit approaches 3 is the same in this case. And that's because when you get closer and closer to 3, nothing weird happens. And we're going to see weird stuff today, but not this example. So if it says x equals 3, that means we're plugging in the point x equals 3 and then finding the equation of that line.
Right, yeah, I understand that. It's just the question said the function at 3.
Yeah, that means x equals 3. It's the same thing.
Okay, okay. Thank you.
Yeah, and that's just, it's just another way of saying x equals 3.
Gotcha.
Yeah, but it's a good question. It's a good question. Any other questions?
I have more of like a formatting question.
Okay.
So about like halfway through, I realized I was way off, and then I like switched gears. Is it better to kind of like erase out, like delete out your incorrect work, or do you want us to leave it there so you can like follow our train of thought?
Okay, so on a quiz, it probably doesn't matter that much because points don't matter much. On an exam, I recommend doing the following. So let me go back to the quiz. Let's say I wrote, for some stupid reason, 3 plus 2 equals 7. Okay. Just to show you that, yeah, oh shoot, that's not right. You know, but you know, maybe I was thinking right. And then I'll just go, oops. And then continue on. And the reason why that's a good idea is that when I'm grading your exams, you'll never get points taken off. Whoops, that was wrong. You'll never get points taken off for letting me know that you made a mistake. Does that make sense?
Yeah,
But if you thought you made a mistake, but you actually didn't, and it was right, but then you erased it, I'll never know what ever happened. I can't give you credit. Do you see that? So my recommendations for the exam is just kind of cross out by writing oops or something like that, you know what I mean? And then continuing on with the right way of doing it. And that way, if you second guess yourself, if you erase it, you can't get credit for it. But if you don't erase it, then you can get credit. Does that make sense?
Yeah, thanks.
Yeah, so that's my recommendation, and not just for my class, from any class. Okay. Okay, any other questions? Feeling taut right about now. Okay. Any questions about anything before we start the new section, 2.2? Okay, let's talk about 2.2. And what we're going to do is we're going to look at what a limit is. So let me give you an example. Let me give you an example of a limit. Okay, so if we want to find, let's say f of x equals 3 minus the sine of x. We want to try and find the limit as x approaches pi over 6 of f of x. So the first thing is I want to mention that this is a standard notation for limits. Nobody writes L-I-M-I-T, by the way. Kind of like nobody writes C-O-S-I-N-E. Everyone writes C-O-S, okay, or S-I-N-E. They always write S-I-N. Okay, so limit is always written this way. You write the 3 letters L-I-M. Below the 3 letters L-I-M, you write down your variable, you write down an arrow, and then you write down what you're approaching. So in this case, we read this as the limit as x approaches pi over 6 of the function f of x, where f of x is 3 minus sine of x. Any questions on how to read the notation of limits and how to write the notation? Okay, well, one of the good things, and I'm going to tell you this works just about always, is that if there's nothing weird about the function, then plugging in is going to work. Okay, now that's hard to prove. That takes a lot of work, but that's a good kind of rule of thumb. So if there's no like dividing by 0 or things like infinities involved or anything weird, then you can usually just plug in and that's your limit. And this is going to be one of those examples, and I'm hoping you can. Can you plug in? And we'll verify it with the graph. But can you plug in pi over 6 and tell me what you get? Let's see if you can put in the chat box. You should be able to do this without a calculator, by the way. If not, then you need to practice some trig. So what happens if you plug in pi over 6? Okay, remember, plugging into the function 3 minus sine of x. And it might have been a while since you've thought about sine of x, but it's time. I don't see everyone jumping in. What's the sine of pi over 6?
Isn't it root 3 over 2? I think Thomas put that in the chat.
That was a good try. That's why I didn't jump in and say great job. That would be the sine of pi over 3.
Oh, yeah, so that's what, 30 degrees, so it's 1/2.
There we go, 1/2. Okay, so sine of pi over 6 is 1/2. 3 minus 1/2, I hope you can do that without a calculator. What's 3 minus 1/2? That's not hard, by the way. That's not a trick question. Okay, yeah, 5/2, 2.5, however you want to write it down. Okay, so that's just like a kind of a rule of thumb that might be true by plugging in and see what happens. That sometimes works, but I'll let you know after today, it'll almost never work to plug in, but today it works. But there's another way of doing it, and that is looking at a graph, and that's a little better. So very easy to jump into Desmos and just type in 3 minus sine of x. And we want the limit as x approaches pi over 6, okay? And you could even do that. How do you get Desmos to show you where x is pi over 6? Anyone know? It's very easy, that's a hint. Anyone know? You know, you just type in x equals pi over 6. Okay, and now we can just zoom in. And we look at it. And guess what? It looks like it's around 2.5. Okay, so there we go. In fact, I can click on that and it actually shows you 2.5. Okay, and what's nice about this particular function is there's no weird stuff going on at the point when x is pi over 6. This curve is just beautiful. Okay, there's nothing funky. Is that clear to everyone? Okay, so one way of finding a limit is to use the graph. Again, you can sketch the graph. You can use Desmos or do it by hand, whatever works for you. You can type in x equals whatever value you want to be taking the limit of. And if everything is good for you, then it'll be like this. Okay? And this usually works. Now, this is not a proof. We're not doing any proofs today, but it's good for visualizing. Okay, you can kind of see, and this is the way I like to look at limits. The way you look at a limit is you say, well, imagine you and your friend. Okay, your friend is going to start over here on the curve on the left. Maybe you're going to start on the right on the curve. And you're going to walk. And you're going to walk along the curve until you're at the x position of pi over 6. And the question is, where do you meet? Actually, the first question is, will you meet? And the second question is, if you do meet, where are you going to meet? What is your y value that you're going to meet? And by the way, if you're going for a picnic, by the way, and there's no picnic table there, that's okay. As long as you're near each other. And you can think of this as COVID times. You're not allowed to hug. Okay, you're not touching each other. You just have to be near each other. Got it? So a little bit of social distancing, and that's good. And we're going to learn something called continuity, where you need the picnic table. You have to be able to hug. But for limits, you don't. You don't need that value to be there. You just need to be on the left and right, really close to each other. Does that make sense? And if you are, you see what the y coordinate is, and that is the limit. Okay, again, that's not a formal mathematical definition. Okay, we'll get there. That's very hard. Today, we're just getting the idea of the limit and how to get a number and be pretty certain you're right. This is not a proof. Okay, Desmos doesn't prove anything, but it gives you the feel that something's probably right. Any questions on this idea? Okay, let me go back. Okay, I have a bunch of examples and we're going to do some. Okay, so that was that one. Okay, let's look at f of x equals 2 minus the square root of x over 4 minus x. And we're going to take the limit as x approaches 4 of f of x. Okay. All right. Is there anything weird going along with this function? What do you think? Are there any issues with this function?
Denominator can't be 0.
Yeah, so one of the issues is we got a denominator and all of a sudden you're used to that. When you get denominator 0, you got a problem, right? There's other possible issues, which isn't a problem on this particular example, but the function could have an issue. If I asked you what the limit as x goes to -4, why is there an issue there?
Because you can't take a square root of a negative number.
Exactly, you can't take a square root of a negative number. So those are really the two big issues in this class when it comes to limits. There's a couple others actually too, but those are the two ones for this section, is that you can end up having a 0 denominator. That's a problem. You can end up having a square root of a negative number. And there's some other issues that you got to worry about. Another one is 0 to the 0th power. I don't know if you realize, but that's a problem. So there are a few other issues, and there's some that are hidden denominators, like the tangent. Y equals the tangent of x, right? It doesn't feel like it has a denominator, but it does. So notice that the tangent is a sine of x over the cosine of x. There's a denominator cosine x, and if that's 0, you got a problem. So there are some hidden denominators that could happen. This particular one, if you plug in, what do you get? What do you get in the numerator?
0.
0. What do you get in the denominator?
0.
0, exactly. What is 0 divided by 0?
For the win, 0.
What is it?
0.
No,
It's
Undefined.
Is it undefined?
it's undefined. Okay, so all of a sudden this has problems. Does that mean we don't have a limit? And this is where you got to think about what a limit's all about. Okay, so again, if you think about what a limit's about, it does not mean the picnic table has to be there for you. We're not plugging in x equals 4. We're starting to the left of x equals 4. We're walking towards 4, but never actually getting to 4. We're starting to the right. We're walking towards 4 and never quite getting to 4. And as long as you don't get to 4, this function has no problem. Do you see that? But you can't find the limit by plugging in 4. It doesn't work. So there's actually 2 ways of doing this problem. The first way is section 2.2. That's where we are today. The second way, I believe, is section 2.3. Okay, so the first way is using graphing. And you, by the way, you're going to like the graphing way, but unfortunately, you have to know the other way too. Okay, just not today, but hold off. Remember, and that's going to be the algebra way. And I'm not going to do that today, but we're going to have to do it later. Okay, so we can graph this function 2 minus root x over 4 minus x. And let's do that. So I can get rid of this, get rid of that. So 2 minus the square root of x, and then divided by 4 minus x. Okay, and as by the way, we notice to the left of 0, there's nothing there. Because remember, square roots have problems. But the good news is we don't worry about to the left of 0. We worry about 4. Now, if you look at the number 4, is Desmos having any problem with the number 4? Okay. It's undefined at 4. We know that. We already looked at it. We got 0 over 0. That's not defined. Okay. Desmos made it not defined. Okay. How big, by the way, is the value 4 in terms of the point? How big is a point? It is infinitesimally small. Our eyes can't see it. So maybe there's a hole there, but it's such a small hole you can't see it. Does that make sense? And if you zoom in a bunch, it's still too small. So Desmos could have done it right. Even though there's a hole there, they didn't exaggerate the hole. We can also write x equals 4 to get an idea, and then we can start zooming. Let's move it up a bit and zoom. And we can see at x equals 4, it's undefined. That's a problem, right? So be careful about doing that, because we know it's undefined. So what might you do? Let's zoom in some more. And don't click on 4. What should I click on? How about something very close to 4, like here? And you get about 0.2503. On this side, you get about 2498. So what might your guess be for this limit? This is 0.2498. This is 0.2503. What might be your guess what the limit might be? And if you want a better estimate, you can always zoom in more. You can zoom in all you want. And 0.25003 and 0.24997. Yeah, so the limit looks like it's around 0.25. Okay. Now, have we proven the limit's 0.25? No, we haven't. In fact, if the limit would say 0.250000001, it would look pretty much exactly the same. Do you see that? So we haven't proven it's 0.25, but we have a pretty good estimate on this limit. Okay, we know it's pretty close to 0.25. We don't know it's exactly 0.25, but that's a really good estimate. Any question on that? Okay, do you think there is going to be a way to prove that it's 0.25?
Oh.
Yes.
Oh.
Yes. Not with graphing though. Okay, there's actually two ways. One is algebra, and we'll do that on Friday. And the other happens in about 4 weeks, I think. That's called a l'hôpital. It's French.
Larry, when you say that we're actually proving that's 0.25, you're saying like because we can't really approach 2.5, right? That's what we're really saying here.
Yeah, because if you hit this value, it says undefined.
Right. Okay. Okay. No, I think I got confused there.
So it
I
looks like we're
understand now.
good to maybe a couple decimal places, right? But we don't know if that 10th decimal place might be something different than a 0. Do you see that?
Yeah. Yeah. I was thinking about it the wrong way.
Yeah. So what we're doing is we're approximating the limit. We're not getting the exact limit with the graph. And that's very important to note, is this is eyeballing it. It's not finding the exact value. But for the real world, eyeballing is usually good enough. Okay. Where do you think limits might show up in the real world? Any thoughts?
Going past the speed of light.
Okay, well, the first thing, you've been watching way too much science fiction. You can't go past the speed of light.
That's exactly what I'm saying, Larry.
But
You
here's
can't
what
do
you
it.
can.
So that's
but
the
here's what
limit.
you can do is you can get close to the speed of light, and you can say what is the limit. So, for example, especially for those of you who are on a diet, don't try and get close to the speed of light. Do you know why? Because you're going to suddenly weigh 1,000,000 pounds. Yeah, and then you're going to feel really fat. You're not fat, but you're definitely massive. So if you actually take a limit in terms of the mass as something goes towards the speed of light, you get infinity. Okay, and we'll talk about infinite limits today too. We'll see what those look like. So there's some weird stuff that goes, and that's one of the reasons why you can't go the speed of light, is you need an infinite amount of energy to get to the speed of light, and an infinite amount of energy is impossible. Okay, and that's because the limit of the energy needed to go the speed of light based on relativity is infinity. And that's a big problem, by the way. Okay, let me give you some other examples. How about in environmental science? Okay, a lot of times what you want to find out is if you do something to the environment, over the long run, what's going to happen? Does that make sense? Okay, sometimes I'll call that equilibrium. You'll also hear that in chemistry, equilibrium. So if you let x equal 1 over the time, then equilibrium is the limit when x goes to 0. And you do a model of your environmental or your chemical situation, and then you let the limit as 1 over t goes to 0, which is x going to 0, and then you find out, for example, how many of these aquatic invasive species you might have in the long run. Does that make sense? Or what is a chemical equilibrium if you put these chemicals together? And that is limits. Okay, I don't know if you've probably heard the word equilibrium before. Okay, and what equilibrium is a limit as 1 over t goes to 0. Okay, or t goes to infinity, either way you look at it. But today we're not doing t goes to infinity, so I'm going to say 1 over t goes to 0, x goes to 0. And that's how you do it. So you write a mathematical model, you take that limit, and that's what you call your equilibrium. Okay, and it works. Okay, and it works. And sometimes it happens really fast. Okay, even though you have to go off to, infinite amount of time, sometimes in an hour, you're close enough that you're done. And sometimes not. And there's a lot of work on that. Okay, so any kind of modeling needs this limit stuff. Okay, and trust me, it does, and I've used it. And again, I've used it for the Forest Service. And we've talked about modeling on thinning forests to see what will happen in the long run after you thin the forest in terms of how fires work, which unfortunately today, all you do is look out your window if you're in Tahoe and you'll know it's important, and it sucks. Okay, but the math is, important to understand, so that if you're working with the Forest Service, for example, you could do the right thing. And right now, we do not have a fire in Tahoe, and I can be happy because I helped that. Okay, I helped making it so that their modeling worked, and their actions towards it, based on that modeling, based on this equilibrium, made it so that we don't get as many fires as we used to get. Okay, so you can trust me, I'm not going to go all the details, but that kind of stuff happens. So limits are really important. Okay, in business, let me tell you where it comes in business. So you probably understand, for example, if you put money in the bank and it's compounded, every month, then there's a formula to find out how much money you're going to have later on. Sounds good? Okay. But if you have $1 and you wait 10 years, then that dollar is going to be worth less. Do you agree? Because of inflation. How often does inflation compound? Always. Okay, continuously. Okay, so you're actually taking a limit as the compounding period goes to 0. And if you take a limit as the compounding period goes to 0 of the financial growth or decay equation, then you end up with inflation. You end up with the modeling of inflation. Okay, and then you end up getting with exponential decay or growth, depending on how you're looking at it. So there's lots of reasons why you care about limits. They come up a lot. The biggie is what we did 2 days ago. Okay, and that is finding the tangent line. And I'm not going to spend too much time. We did that 2 days ago, but that's the biggie for limits. And we're going to be doing that a lot in a big way for all quarter. So any questions on why you care? Okay. All right, so now let's go and do some more limits, because that's what today is all about. What's the wrong one? That was that one. Okay, so we just found this limit. And by the way, I'm not gonna write equals, because we did it with a graph. And we do it with a graph, you gotta be careful about equals. So instead, I think it's that guy. That one. Do you know what that symbol is? Kind of a line with a little curvy thingy?
About.
Yeah, approximately. Okay, now it turns out it is equal, but from what we saw, we can only say it's approximately 0.25. And maybe write based on the graph. Any questions on that? So today we're only doing approximate, unless we're in this case where there's nothing wrong and then you just plug in and you're done. And I guess I should write down the answer to this one. That was equal to 2.5. So I want to note that there's a difference in approximately equal to. That means that we've approximated using a visual versus just plugging in and getting the answer because we know it's right. Okay, whereas plugging in on this second one doesn't work because you get 0 divided by 0, and that's just undefined. But the limit looks like it might be 0.25, and it turns out it is. Okay, then there's a table way. How about sine x over x? So if you look at sine x divided by x and you plug in, wait, I don't want to do 5, 6. That was a copy and paste error. Plug in 0. What do you get? What do you get if you plug in 0? Always cross your fingers and hope you get something nice, and then you're done. So what do we get if you plug in 0?
It's undefined.
It's undefined. And that's because sine of 0 is 0. You're supposed to know that, by the way. And again, that's not calculus, that's pre-calc. So you're supposed to know some pre-calc and basic pre-calc. And so you get 0 over 0. 0 over 0 is undefined. Okay, but we saw before that doesn't necessarily mean the limit doesn't exist. It just means we have more work to do. So let's use a table on this one. And to use a table, what we do, let's make a table. Yep. Maybe I'll do 4. So we're going to have x, and we're going to do sine x over x. Okay, and what we want to do is we want to pick things near 0. So maybe 0.001. And let's plug in sine x over x. So I'm just going to put it here. Sine of 0.001 over 0.001. What do I get? I get 6 9s and an 833. Any questions on that? Okay. What happens if we plug in? How about negative 0.00? I don't know. How about 2? It's good to do some kind of randomish numbers actually, so you don't get into some tricky problems. And all I have to do is change my numbers there on my search bar. Put a negative there. Put a 2. Put a negative there. And put a 2. And look at that. 6 9s and 3 3s. Okay. Maybe we'll try, how about 0.0005 and see what we get. And I get one more 0. Seven 9s and a 5 and an 8. Okay, so now we can guess at the limit. What do you think the limit might be? And we're guessing based on our table. So I'm going to use the approximate number because it's an approximation. I like this approximation better, actually. Yeah, 1. See, you could say 0.99, but if you round it 2 decimal places, that 9 builds it up to a 1. You see the third 9 makes it a 1 on all of these. So our guess is that this is 1. Okay? But this is an approximation. It's not a proof that the limit is 1. Okay? It might be 75 9s and a 7 or something. You would never know from this table, would you? But it turns out it is 1.
So no matter what, how many numbers are on the decimal, like past the decimal point, it can always approximate to 1, the value.
Yeah, if I tried some more, you'll see it'll be real close to 1, no matter what. You'll never get over 1. And yeah, you'll never get over 1, it turns out. Again, I can prove it, but I'm not going to today. But you're going to get things that look like this every time. And the more zeros you put in, before the number, the more 9s you're going to see. Okay. Again, what matters is that you can put in a table, and if you keep getting a number very close to some nice number, then that's probably the limit. But I'm using the word probably, not definitely. Any questions on that? Okay, so that's another example. It's a table example. Okay, the next example is a piecewise defined function. So here's an example of a piecewise defined function. And this is f of x equals the function 4 minus x squared if x is not equal to 1, 2 if x equals 1. Okay, first thing I want to let you know in Desmos, this is how you do piecewise function. Is kind of messy in Desmos. And honestly, I didn't exactly know how to do it. What I did is I went to Google and I typed in piecewise function Desmos. It gave me a nice example and then I knew how to do it. And again, hopefully you're good enough that you know how to do internet searches also. Okay, the internet's been around long enough. When I first taught, I couldn't say that because no one knew what the internet was except me. But now you all know. So the way Desmos works, by the way, is you put y equals, you put a bracket called a curly brace, and then you put x, the inequality, and then you put a colon, then you put what the function is. So it's kind of backwards of piecewise, the way you write piecewise functions kind of algebraically. Then you put a comma, then you put the next inequality, colon, and the function for that inequality. So ours, just to remind you, was 4 minus x squared not equal to 1, 2 for equal 1. So I should write x is not equal. And I believe not equal to is that. Is it? Nope. It may not handle not equal to 1, but that's okay, actually. I think I'm going to do a different Desmos. I want to show you how to do piecewise anyway. We have 4 minus x squared. And that's for it not equal to 1. And then if it's equal to 1, it's 2. So it's at the point 1 comma 2. So I should probably plot the point 1 comma 2. Whoops, I think I did the wrong one. One more try. There. And let's zoom out. Whoops, wrong way. Okay, there we go. So there's a hole right here. And there's a point here. And we want the limit as x approaches 1. So what is the limit as x approaches 1? What's the limit as x approaches 1? I can even write x equals 1. Huh?
Would it be undefined because it's a vertical line?
Remember, it's a limit of this function, which is a piecewise function 4 minus x squared for x not equal to 1, and it's 2 for x equal 1. So the vertical line just helps you visualize, that's all. Okay, and the idea is you got to go back to the idea of the limit. Okay, you got to go for that, meeting your friend example. If you're on the left, if you're on the left and your friend is on the right, and you walk towards each other, are you going to be able to say hi? What do you think? I don't see y'all jumping in. So if you're walking along the curve from the left and your friend is walking from the right, are you going to be able to say hi to each other when you get near
No.
1? The answer is yes. Okay, there's going to be no picnic table in the middle for you waiting. The picnic table is way down here, but it doesn't matter. You don't care about the picnic table. All you need to do is say hi. Remember social distancing. You're never actually going to get exactly at 1. You're going to get close to 1, but not exactly at 1. And what's your y value where you're going to be close to each other? It's going to approach 3. So that limit is 3. So I want to emphasize something. So first, let's write down 3. So the idea here is that if you look at the specific value at x equal 1, it's meaningless. You could ignore it because all that matters is left and right, it's always 4 minus x squared. And if you plug in 1 into that, you get 3. Anyone lost on that reasoning? So having a hole is not a problem. Okay, what if, on the other hand, let me do one more, something similar. What if we had the following? How about 2 plus x for x less than 1? And how about x for x greater than or equal to 1? Okay, now it's a whole different story. So let's work that out. So now I'm going to go to this piecewise, 2 plus x and x. And what is that limit as x approaches 1? Now we can look at the graph, and now imagine you starting on the left, your friend starting on the right, and you're going to go until you reach your x coordinate of 1, and you want to say hi to each other. What's going to happen? Yeah, this one does not exist. Okay, it's kind of like you're on different roads. You're never going to see each other. You're not anywhere close. Imagine this is hundreds of miles. Let's call that the units. Well, you're going to be 200 miles away from each other when you get close to 1. You see how that works? So this one does not exist because these functions are far from each other on the left and right at x equals 1. So I'm going to do the following. So first thing, I didn't change that. It's not equal to 3. It's equal to does not exist. And I am always going to use D&E. And so does the computer program, by the way. If it doesn't exist, you write D&E in capital letters. Any questions on that example? Okay, so now we have another example. The next one is, let's suppose f of x equals 1 over x for x greater than or equal to -1, and ax plus 2 for x less than -1. And the question is, what value of a is there a limit? Or let's go, does the limit exist? Any questions on the question? Any questions? To make it look like an A. All right, well, how do we go about this one? Any thoughts? I don't see y'all jumping in. Okay, the idea is if you use the left-hand side or the right-hand side and you get close to -1, you should get close to the same value. And if you get to -1, there's no issues for -1 for 1 over x. 0 is the only issue for 1 over x. -1's not a problem. Ax plus 2 is a line, also not a problem for -1. That means we're plugging in. So what we're going to do is we're going to set them equal to each other. We're going to say 1 over -1. Let's write it nicer. 1 over -1, we're going to set equal to a times -1 plus 2. And then it's basic math. So what do you get? What is A? You're all supposed to know how to solve that problem, by the way. Try this again. What's A equal to? Yeah, so A equals 3. Because if A is 3, it works. So at A equals 3, the limit exists. If A is not 3, the limit does not exist. And by the way, if A is 3, the limit is 1/3. I'm sorry, it's x equals -1. So then at x equals -1, let me double check. So you have -1, yeah, 3. So at A equals 3, what do you get? Hopefully it works. -1, let me double check. And then it works. Any questions on that? Okay, so I have some more to talk about. What about the limit as x goes to 0 of f of x if f of x is 1 over x squared? What happens if we plug in 0? What do you get?
Doesn't exist. Undefined.
Doesn't exist, but it's a special doesn't exist. So let me go in Desmos again. And let's go and do 1 over x squared. What happens if you and your friend come from the left and right and walk towards 0? Where are you going to walk?
Parallel to each other.
Yeah, are you getting close to each other? Kind of. Does that make sense? You're getting up to infinity. So even though infinity is not a number, it's important. So you can, it does not exist is technically correct, but not as good as infinity. There we go. So this is equal to infinity. So you could get infinity and you can get negative infinity. You get infinity if you have a vertical asymptote where both sides go up. Okay, I'm not going to do, we don't have much time, so you get negative infinity if the same thing happens but both sides go down. Does that make sense? So I'm going to quickly mention one more thing that comes up once in a while, and that is you can take limits from just one side instead of both sides. So the notation for that, there's an example. It says f of x equals the square root of 3 plus x. And notice it says limit, and we have x approaches, that's that arrow, -3. And see this superscript plus? That means from the positive side, often called from the right of f of x. So the idea here is that this function f of x, you can't even talk about the limit as x goes to -3 in general because there is no left side. Because the square root doesn't work if you're to the left of -3. Is that clear? But you can talk about it from the right-hand side. So if you're on the right-hand side of -3, then 3 plus -3 gives you 0. And as long as you're on the right-hand side, there's no issues. But the left-hand side, there's an issue. So if you had the limit without having the plus, you'd say does not exist. With the plus, then it's just going to be the square root of 6. Any questions on that? Similarly, in the next example, I have a little not minus sign there. So x goes to 0 from the left. So that means we're going to let x be slightly negative. And what do you get if x is slightly negative when you have x over the square root of x? The idea is the square root of x multiplies x by -1 if x started as negative. So if you take x over -x, that gives you -1. Okay. If this were a plus instead of a minus, it would be +1, it turns out. If it didn't have that superscript, it would just be does not exist. And those are called one-sided limits. So limit from the left and limit from the right. Any questions on this idea right here? Any questions? Okay, we're going to, I don't know if you remember. Do you remember what I told you what's happening right after this class today?
Office hours.
Nope, not
Math
today.
club.
Today's special, math club meeting. Yeah, and we're gonna have our math club meeting. And we even have a few people who are from last year who were in our math club and want to continue on. So I want to let you know this is a math club. It's a really good thing. I don't give you points for this class or anything, but you get points in your soul. Let's put it that way. And you get to like hang out with people, help out children, which is good, do some fun stuff. But you're welcome to leave if you need. When we're done with our math club meeting, I'll go into office hours. And that, it probably won't be more than 20 minutes. Okay, and I'll be up on Zoom for an hour and a half or so from now. So that is the plan. So, but again, I recommend that it doesn't take much work to be in the math club, by the way. And there might be some volunteering to do, helping out children. I'm working with the district. It's hard. COVID times are so hard to make this work. So I'm going to work with the district. I might work with Boys and Girls Club also. There might even be some face-to-face tutoring if anyone's okay with that. And if you're not, you don't have to do it, by the way. Because the Boys and Girls Club actually is meeting face-to-face. You'd have to wear a mask. So we're losing some people, but we're keeping a bunch, which is good. Oh, you know what? I almost forgot. I need to stop the recording. So thank you for coming. I'm stopping our recording.